Okay. So there is something like a OK button that I think you have to check. Okay. Okay, Abu. So
Yeah.
you
Yeah.
tell me that what are your two favorite subjects?
Fluid mechanics and basic thermodynamics.
Fluid mechanics and basic thermodynamics. Fine. So okay. So can you? Okay. I hope that you have a. I mean, copy and pen. So can you draw a venturimeter, an inclined venturimeter? Can you draw
Inclined
an
measurement.
inclined? Yes. I mean,
Yes, yes.
suppose that you have a, I mean, inclined pipe, and in that pipe you have a venturimeter. So you have to draw an inclined venturimeter.
Okay.
Yes.
Where the draw?
Show me, show me, show me. Okay. So you also show the flow. I mean, the flow directions. Okay, fine, fine. Now tell me that. I mean, what I mean, why the venturimeter is made asymmetric, and which angle is. First of all, you tell me that which angle is, I mean, shorter and which angle is larger, the upstream angle or the downstream angle. So here I am also drawing the same thing what you have drawn. You have drawn it something like this, right?
Yes.
Okay, fine.
The upstream angle is more than the downstream angle.
So what is upstream? I mean, have you
I
I
mean,
so this is upstream. So okay, now this is I am actually naming the sections. Okay, so this is my section A, or I think I should draw it like this. There is my section A, section B, section C, section D, section E. So you have to tell me that which angle is, I mean, shorter. This angle from B to C or from D to E. Which angle is shorter?
angle between
B
angle
to
between
C.
B to C is more. B to C is more.
More, more. Okay. So this is called upstream. Okay. Upstream means, I mean, before the flow. Okay, fine.
Yes.
So now you tell me that why the angle from D to E is made shorter than from B to C.
Because uh, because the pressure at B to C is decreasing,
Yes.
and velocity is increasing, and
Mm-hmm.
after that the throat in which the velocity becomes maximum
Mm-hmm.
and the pressure becomes minimum, and to graduate the diverging part from the throat,
Mm-hmm.
we have to diverge the suction in such a way that there will be there is no adverse pressure gradient formed or the turbulent eddies, due to which there might be some inaccuracy in the measurement of flow. That's why we
Okay.
diverge it in a long section.
So okay, so you are telling that we don't want the adverse pressure gradient,
Yes.
but you actually, I mean, you cannot avoid the adverse pressure gradient. There will be some adverse pressure gradient. So I mean, if
Yes.
you are using a diverging section, there will be some adverse pressure gradient, right?
Yes.
So why? I mean, why cannot I? So if this is my alpha, if this is my alpha, so maybe sorry, yes. If this is alpha, okay. So I mean, why cannot I make it alpha? Okay, there will be adverse pressure gradient for sure. Okay, but is
Yes.
there a particular condition that the adverse pressure gradient imposes? Like, for example, this this part, could have been like this or this or this. So you are telling that and I need a diverging section, but I don't want, I mean, adverse pressure gradient. But that is not possible. You will have adverse
Yes.
pressure gradient, right?
Yes.
So why
Sir,
I cannot give the same alpha?
sir, if I make the same alpha like that is present in the converging section, then but the flow cannot graduate from the thin section to the constant diameter section in such a way uh, that the flow is like if I made this diverging section in a longer part, then the flow will be streamlined and smooth. Uh, that's
Okay,
and the flow can
okay,
happen in a more arranged manner.
more arranged manner. Okay, leave it. Okay, so now Abu, what you have to draw is you have to draw the pressure variation from, I mean, across this direction. Okay, so if this is my x direction, okay, you draw this P versus X. Okay, you draw the P versus X. So like you have to draw it like this. First you show A, then B, then C, then D, then E. Okay. So likewise,
Yes.
you draw some lines here and you have to draw the variation. Okay, draw it.
Um, Dada, can you show the diagram?
Yeah. This is the same diagram that you have drawn, right? Hmm.
In the section A to B, the
Hmm.
pressure will sorry, in the section B to C, the pressure will decrease. Pressure will decrease
You,
non-linearly.
you first draw it. You first draw it. Draw it and show me. What? Just what this dominant. Mm-hmm.
In the section B to C, it will decrease.
For A to B, for A to B,
For A to B, okay. For A to B, it will be constant.
for A to B, it will be constant, right? Okay. For A to B, it will be constant. Okay, fine. So now you see what you have drawn is that from D to E, right? There is so if I take a pipe like this, okay. So this is a pipe like this, and I am joining it. Okay. So you have already drawn that your pressure this at this point is higher than the pressure at this point, right? You have drawn it already. So now you have to, well, I will just make it. Yeah. Okay. So you have shown that the pressure at this point will be higher than this point. Now you tell me that if I join this pipe here and if I just open these things like, okay. So now you have to tell me that what will be the flow direction, I mean, in this pipe. I mean, will it be from like this to this or like this to this? So if I mean, if I call these points as 1 and 2, so you have to tell me that in this green pipe, what will be the flow direction from 1 to 2 or from 2 to 1? You have to tell with the logic.
Okay. Uh, in this section, that means we haven't put any other manometric liquid in the manometer, or
No,
it
no, no,
is
no, no,
only
no,
water
no.
flow.
Yes, yes, only water flowing. There is no fluid inside the green pipe. Okay, I have just joined a green pipe. So you have to tell me
Okay.
that. Well, yes, tell me.
Yes, since the pressure at 2 will be more than the 1,
Mhm.
so the fluid will go inside that manometer. So the flow can be from 2 to 1.
Flow can be from 2 to 1. Okay, Abdul. Okay, fine. Now we will move to the heat transfer. You said heat transfer, right? Fluid mechanics and heat transfer.
Basic thermodynamics.
Okay, sorry, basic thermodynamics. Sorry. Okay, so basic thermodynamics. Now we will do. So okay, you draw it. Um, okay, so let us say that I have a beaker. Okay, I have a beaker, and now what I have done is I have poured some water here. So this is water. Clear? This is H2O at room temperature, at your room temperature, maybe 25 degrees Celsius at 1 atm pressure. Clear? So first I am applying heat. Okay, I'm applying heat. So you have to draw the the temperature versus time of this water.
Okay. Hello.
Yeah, show me. Just wait a minute. Yeah, show me temperature versus time. Okay, so why that is a flat zone? I mean, why there is a flat zone?
Yes, in 100 degrees Celsius, since it is one atmospheric pressure, then
Mhm.
100 degrees Celsius, there will be phase change from liquid to vapor.
Okay.
So, and it will fit
So
the region of
right. Okay, fine. And other than that, will they? I mean, will those are straight lines? I mean, are they straight lines? The increasing lines, other than the flat line, are they straight lines? Other than the flat
yes,
lines, the two lines, are they straight?
yes, they are straight, but their slopes are different.
Why? Why the slopes will be different?
So, because the specific heat of liquid and vapor are different.
Which is more?
Specific heat of water is more, so it will have less slope.
Are you sure?
Yes.
Okay. Okay. So now you okay. So now what I am just doing is I am putting okay. So at this position I am putting a lead. At this position I am putting a lead. Okay. Just hold a minute. Okay. So at this position I am just putting a lead. Okay. This is a solid lead. Okay. So I mean initially I was having 1 atm pressure. Initially I was having 1 atm pressure. Now you draw the same T versus T graph for this case when I am having the lead on the same plot. Okay, you draw that.
And uh, initially it was pressure was 1 atm, and now
Yes,
lead is placed.
yes, and I am supplying heat.
Okay.
Okay, one more thing, and you have already assumed it. I think that through these surfaces I don't have any heat transfer. Okay,
Okay.
okay.
Uh, initially after the heat is added into the container, uh,
Hmm.
there will be
You
initially
draw
the
it and
initially
explain.
the
You you draw it and explain. Then explain.
the graph will be same, but the phase change will occur at a pressure more than the initial one.
The phase change will occur at a pressure more than the initial one. At a pressure more than the initial one.
By pressure, I mean the saturation pressure.
Mm-hmm. What is the saturation pressure?
It will be more than the over atmospheric pressure, obviously.
No, you have to draw the temperature versus time. That you have to draw. Okay.
Yes, since saturation pressure is increasing, so the saturation temperature will also increase in the phase change, during phase change. So the phase change will
Saturation temperature will increase. Okay.
yes,
Fine.
the phase change region.
Okay. You draw it on the same graph.
Yes, it will be like the earlier graph, but the phase change will occur at a temperature more than 100 degrees Celsius.
Just wait. No. You have to draw it in the same graph. Okay. Same plot. Same plot. You have to draw it. This is temperature versus time. And now you are showing that the vapor is forming at a lesser time. Why? The vapor is forming at a lower time, and why that is so? I mean, now the plateau region is, you have shown it as a lower plateau region. So why that is so?
Uh, because as we increase the pressure, the saturation temperature corresponding to that point will also increase, and due to which latent heat of vaporization will decrease.
Okay, good, good. Okay, fine. Now, now, okay. Now, if what I will do is, if other than the lead, this was a moving piston. Other than the lead, this was a moving piston. Okay, this is a, I think you can see it.
Yes.
Sorry. Other than the lead, this is a moving piston. Okay.
Okay.
Now you draw the same graph. Temperature versus time.
Means the pressure inside will be 1 atmospheric as it was before, or what?
Hmm. Initial at time t equal to 0, the same 1 atmospheric pressure was there. Okay.
Okay. Graph will be like the previous case, the first case, in which the boiling was occurring as at 100 degrees Celsius, because in this process there will be isobaric heat addition, so the saturation pressure will remain constant, and due to which the saturation temperature will also be 100 degrees Celsius. If we assume the process is quasi-steady process,
And if we don't assume the, process to be quasi-static, then what will happen?
then the pressure which we assumed as 1 atmospheric pressure initially will not be same at every intermediate points. So we have to.
Okay, you can actually, you can, yes, yes, put the copy. Okay. So what is a quasi-static process?
The quasi-steady process actually internally reversible process which is a very slow, infinitesimally slow process, in which at every intermediate points the intensive properties remain uniform throughout the system.
In every intermediate points. Okay.
The
So
intensive property.
can I okay, so can I have a quasi-static process which is irreversible?
No, quasi-static process is internally reversible process.
Internally reversible process. What do you mean by internally reversible process?
And, it means there will not be any losses or occurred inside the system. Will not be any reversibility associated within the system.
Okay, so for this system, okay, if I have the friction between the piston and the cylinder wall, will it be a quasi-static? I mean, can I achieve a quasi-static one, quasi-static process if I have
Uh,
a friction here?
Friction between the piston and the boundary.
Yes.
Okay.
Here.
Uh,
Here.
then,
Here.
then
Can
yes.
I have?
If we take the system as both piston and the cylinder,
Mhm.
then we can't assume because there will be losses in terms of reversibilities.
Okay. Okay. Fine. Fine. Okay. So now you tell me, can you write or just tell me the first law for any system, first law of thermodynamics for any system? Can you tell me?
Yes, for first law for thermodynamics states that uh, the net heat interaction will be equal to the net
No, no, no.
work
Just
exemption.
mathematically. Yes, mathematically. Okay, okay. You tell me. Mathematically, you tell.
Uh, uh, Q is equal to delta U plus del W.
Q equals to delta
Delta
E.
E plus del W.
Delta
Delta
E.
E
Okay, okay.
plus
Delta
plus
E
del W.
plus. Okay, so what is this E?
E is the energy. It associates both microscopic as well as the macroscopic form of energy. That is kinetic energy, potential energy, and the internal energy.
Okay, fine. Okay, Abbu. Now we don't have that much time, so now let me give you the feedback. Okay, so I will start with first the thermodynamics portion. So I will appreciate here that you have actually a very good fundamental in your thermodynamics. Okay, so basically they will start from this type of questions only, either the piston cylinder question or the phase change question of obviously water. So water is their very much I mean favorite fluid. Okay, so they will only ask from water. I mean, at least 90% sure. Okay. So study the phase diagram of water very well. That you have, I think, already studied very well and very good. So you have answered almost all the questions, I mean, correctly in thermodynamics. Just only one question, and it is actually a very, I mean, in-depth question. See, quasi-static quasi-static process only means that the process is extremely slow. Okay, it does not have anything to do with the reversibility. So there exists quasi-static irreversible processes. There exists. Okay, but if you have to find the work done, like you if you want to write the work done like P internal into dV, then you have to have that the process should be firstly quasi-static, secondly it should have the reversible nature. Okay, so this is actually possible. What I was asking you, that if I have friction here, then also the process can be quasi-static, because quasi-static means the process has to be very slow. That you can always do. But if there is friction, you cannot write that my P external is equal to P internal, because if you now draw the FBD, the free body diagram of this piston, there will be friction forces. Then there will be a difference between P external and P internal. Okay. Then if you have the friction, you cannot write as your work done as PDV. But quasi-static irreversible processes are, they exist. Okay. Other than this, you have answered almost all the questions very good. Okay. Okay. So now let me tell you about the fluid mechanics. So first of all, everything was almost right, but see, this question is also very, I mean, one of the, one of the trademark questions, this venturimeter question. Now you see, you first tell me that, how can I know that what is the direction of a flow? What is the direction of the flow of a fluid? How can I know? Is the if pressure is the only governing parameter? Is pressure is on, then what is the governing parameter?
It is a net mechanical head at a point.
Exactly, net mechanical head at a point. So when you are already telling that the fluid is flowing from 1 to 2 like this, then you are telling that at 1 the total mechanical head must be more than the head at 2.
Yes.
Okay, then this flow, cannot take place like this. Okay,
Yes.
because when you have already asserted that my flow is in this direction, that means my mechanical head at 1 is more than the mechanical head at 2. Then at no situation the flow can occur from 2 to 1. Okay, so in BARC they will actually tell you like this: either you will place very good panelists, good means they will not, behave very bad. Okay, so they will just first just okay. Okay, so in BARC you will get two types of panelists. First, they will actually behave very good. Okay, but the but the moment I say good, that means if you answer anything wrong, they will not tell you that okay, this is wrong and everything. They will actually smile at you that okay beta, okay, chalo aage badhte hain. Okay, so when you will answer anything wrong, you will see that they will give only maybe one chance or two chance. They will give you some hint, but they will they will say okay, chalo ab, we will now we will move into the next subject. Okay, and the second type of panelists, they will actually mock you or actually pass some bad comments. Okay, that क्या सच में ऐसा होगा? Okay, ऐसा कुछ, they will actually try to make you uncomfortable. There are some, there are few panelists like that also. So in that situation, you have to keep your mind very calm. That is a challenge. Okay, have you understood?
Yes.
Okay. So
Yes, sir.
for fluid mechanics, you know the thing I know because you only told me that the direction of the flow will be, will be obtained from the total mechanical head and not from the pressure. I know that you also know that, but at the interview situation, think a bit more. Okay, because you see that you already knew the thing, but still you answered it wrong. Okay. So that was from my end, the opinion. Do you have anything to ask?
Yeah, I have to ask one question. Like
Ask.
my like it is related to my project.
Okay, okay, okay.
Uh, uh, my college project was based on quantum metallurgy technique, and I have
Mhm.
heard that in BARC interview, and if someone's project is getting published, then they it becomes an edge. So, but I am not very much confident about the quantum metallurgy technique. If they
Project,
ask anything without
project.
yes.
I don't know that from where you have heard it, but it doesn't matter. Honestly, doesn't matter. I mean, what have you done up till in your life? It doesn't matter if you are get AIR 1, if you have cracked your board exams with very good rank or not, if you have published a lot of papers or not. It does not matter at all. Okay, 100% weightage is on your interview. Okay,
Okay.
it doesn't matter that if you have published a paper or not. Okay, I don't
Okay.
know that
Okay.
from where you have heard it, but it, I mean, yes, it does not matter. Everything is up to your interview. everything, 100%. What you will perform in the interview, on that they will judge you. Okay.
Okay. Okay.
Okay then. Any more questions do you have?
No, for now it is fine.
Okay. And how did you feel? So was worth, I mean,
It was,
was spend, so is spending, I mean, rupees 249 was worth for it or not?
it was a really nice experience because I have given an interview after a very long time. I appeared in the campus placement interview last year. It has been 1 year.
Okay, 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 okay. So did you enjoy this interview? Did you learn anything?
It- yes, yes. I
Okay,
really.
okay, okay. So I will also, I mean, I would also like to meet you again. Okay, in any other mock interview. Until that, goodbye, take care, and thank you. Bye.
Thank
Okay,
you. Thank you, Dada.
bye, bye.